Welcome back to Neural Intel. Today, you've sent in some really cutting-edge research. It's all about how sequence models learn and remember.
That's right.
And we're going deep to unpack what it all means for the future, focusing, as always, on the core technical stuff.
Indeed. The main paper we're looking at is titled It's All Connected, A Journey Through Test Time Memorization, Attentional Bias, Retention, and Online Optimization. Quite a mouthful, but fascinating stuff.
Ah, yeah.
And we've got the figures and tables, too, which really help visualize things.
Exactly. So our mission today, really get under the hood for you. Understand the framework behind how models like transformers, RNNs, how they handle memory.
And explore some of these surprising new technical approaches the paper brings up, things that could really push their capabilities.
Okay, let's jump right in. The paper starts by, well, it reconceptualizes neural architectures as associative memory modules. Let's unpack that. What does that mean, fundamentally? And this connection to attentional bias in humans.
Well, the associative memory angle is key. Fundamentally, it means seeing these networks as systems built to learn mappings, between keys and values.
Like associating a face with a name.
Exactly like that. And the paper draws this really neat parallel to human attentional bias, how we naturally focus on certain things. For sequence models, this attentional bias is basically the model's internal memory goal, what it's trying to achieve when learning those key value links.
So the models are learning to connect the dots, sort of like our own memory. But what's the paper's key insight into how they do it? There's this equation for MMA, LMKV. So what are K and V here, the keys and values? And what about L, the objective function?
Right, so think of keys K as specific bits of info in the input sequence at any given moment, and values V are what the model needs to link to those keys to do its job, like predicting the next word, maybe? And L, the objective function, they call it the attentional bias. It's basically the yardstick. How the model measures how well it's learned in memory, M, maps those keys, K, to the values V. The goal is to find the memory that makes L as small as possible, learning the right connections.
Got it. Now, here's where it gets really interesting, I thought. The research found, surprisingly, that most existing models, they rely on just two main things for this attentional bias.
Yeah.
Either dot product similarity or O2 regression.
Yes, that was a surprise.
Why is that so surprising? And what's to tell us about how we've been designing these things?
Well, dot product is everywhere in attention, right? And O2 regression is super common for training networks. The surprise is that all these different architectures, transformers, linear RNNs, you name it, seem to boil down to one of these two fairly simple biases.
Huh.
So despite all the hype around new architectures maybe under the hood, many are still using fundamentally similar ways to learn memory associations. It suggests we've been looking at different buildings maybe, but with very similar foundations. That realization could be a big deal.
Okay, shifting gears a bit. Forgetting. The paper has this new take. Forgetting isn't just passive decay. It's like a form of retention to regularization for the attentional bias. How did that change things? Is it like the model actively decides what's important?
Exactly, that's the shift. Instead of just fading away, framing it as retention regularization implies forgetting is an active process. The model prioritizes what to keep based on this implicit regularization.
Okay.
Basically, this term penalizes big changes to the memory, encouraging it to hold on to old mappings unless there's a strong reason to update. Think of it like cleaning out your attic. You don't just randomly forget stuff. You prioritize keeping important things and maybe discard things you haven't needed for ages.
That makes sense. So if it's active, can we control it better? That leads to these retention gates, right? What are they for? How do they help balance learning new things versus keeping old knowledge?
Precisely. These retention gates aim for more fine-grained control. It's all about that classic machine learning problem, the stability-plasticity dilemma.
Right, learning new stuff without wrecking the old.
Exactly. These gates can dynamically adjust how much that retention regularization influences things, based on the input and the current memory state. The goal is to avoid catastrophic forgetting, where learning something new wipes out useful old info but still let the model adapt.
So building on these ideas, attentional bias, retentional rate, the researchers proposed this framework, Miras, a new way to actually design these architectures based on 4 key choices. Figure 1 lays it out nicely. What are these choices? How does Miras help structure thinking?
Miras provides a really structured way to approach sequence model design. It breaks it down into 4 core decisions, like you see in Figure 1. First, 1, the associative memory architecture, the basic structure holding the memories.
Okay.
Second, 2, the attentional bias objective, that internal goal we talked about. Third, 3, the retention gate, the mechanism controlling forgetting, or rather retention. And fourth, for the memory learning algorithm, how the memory actually gets updated.
So it's like a blueprint with 4 main parts you need to decide on.
Exactly. It gives a unified view of existing models and a clear roadmap for creating new ones.
Can you give some quick examples for each, from the paper or figure 1?
Sure. For memory architecture, Figure 1 shows things like simple vectors, matrices, MLPs, multi-layer perceptrons, or even fancier stuff like memory mosaics.
Right.
For 2, attentional bias, you've got options like regression, dot product, Huber loss, KL divergence. For 3, retention, they mention things like Rahita regularization, elastic net, KL divergence again, Bregman divergence.
Lots of options.
Yeah. And finally, 4, the learning algorithm could be standard gradient descent, GD with momentum, Newton's method, or even non-parametric approaches. Table 1 actually maps a bunch of existing models onto these choices.
Yeah, that table's super useful. Okay, so Miras leads them to create 3 new models: Moneta, Yaad, and Memora. What's the design thinking behind each, especially their choices for attentional bias and retention?
All right, these 3 really demonstrate Miras's flexibility. Moneta tries to move beyond that simple Ito-2 bias, remember the surprise. It uses an O no norm objective, instead that's equation 10. And for retention, it uses a kind of hybrid ODO and O2 regularization. The update's in equation 24.
Okay, so different bias, different retention for Moneta. What about Yaad?
Yaad is built for robustness. It uses Huber loss for its attentional bias, equation 16, which is less sensitive to outliers in the data, and its retention combines local and global ODO regularization. Update rules, equation 26.
And Memora.
Memora draws inspiration from elastic net regularization. It uses O2 regression for bias, but its retention gate uses KL divergence, equation 21, leading to the update in equation 27. So, yeah, you see Moneta, Yaad, Memora each making distinct Miras choices, exploring different design combinations.
Table 1, like we said, maps existing models too. Can you maybe point out 1 or 2 examples from there just to see how known models fit?
Absolutely. If you look at table 1, you see models like RetNet and Mamba. They fit into Miras as having vector or matrix memory, using dot product similarity for bias, and simple O2 regularization for retention, trained with GD.
Okay, familiar names.
Then you have others like DeltaNet or Longhorn. They also use matrix memory and E2 regression bias, but Table 1 notes they lack an explicit retention gate in the Miras definition used there.
Interesting distinction.
And one more, Titans. Uses an MLP for memory, U2 bias, U2 retention, but trains with GD plus momentum. So Miras really helps categorize and compare these different approaches using a common language.
Let's get to the results. How do these new Miras models actually perform? The paper claims exceptional performance, even beating transformers and other modern recurrent models. What's the evidence in Table 2?
Table 2 is pretty compelling. Across different tasks, language modeling measured by perplexity, common sense reasoning like PQA, HeliSwag, question answering like ARC, Bulky Moneta, Yaad, and Memora consistently show strong results. Compared to baselines like Transformer++ and recent linear RNNs across various model sizes, 340 million, 760 million, 1.3 billion parameters. Often, even the non-hybrid versions of these Miras models are very competitive.
Okay, strong numbers. Now, Figure 3 looks at scaling. How do Moneta, Yaad, Memora stack up against baselines like Transformer, Mamba 2, GSA, TTT when you increase model size or sequence length? Especially the longer context part, they seem better there.
Yeah, Figure 3 is revealing. The left panel shows scaling with compute, FLOPs. Generally, the Miras variants are competitive there, but the middle and right panels show performance as context length grows. And there, particularly for the 340M and 760M models shown, Moneta, Yaad, and Memora generally show better scaling. Their performance degrades less or even improves more as the context gets longer compared to some baselines.
Why might that be? Does it suggest something about their architecture? That they benefit more from longer context?
It likely comes down to a combination of things. The more expressive memory architecture, they often use MLPs instead of simpler vectors matrices. Plus, those novel attentional bias and retention choices seem to allow for more effective memory management over these really long sequences.
Makes sense. Okay, Table 3 focuses on the needle and haystack task, NIAH. What do those results tell us about recall and effective context window for the Miras models? And why might Moneta do particularly well with synthetic noise?
NIAH is brutal. It specifically tests finding a small piece of info buried in a long text, haystack. Table 3 shows Moneta, Yaad, Memora performing strongly across different context length, up to 8K tokens and different kinds of haystack noise. They often beat the baselines.
Suggesting better recall and longer effective context.
Exactly. As for Moneta doing well on synthetic noise, SNIHPK, it might suggest its specific combo, the UD bias, and that hybrid OH2 retention is particularly good at filtering out irrelevant junk and holding on to the crucial needle.
Interesting. Figure 4 digs into Moneta's parameters. Phi from the auto bias and Q from the auto retention. What's the takeaway from how tweaking these affects performance?
Figure 4 shows these choices matter. The left graph suggests an optimal p-value around 3 seems to work well across different context lengths for Moneta. The right graph, looking at Q for retention, shows it also impacts performance, and maybe even how performance changes with context length. So tuning the retention mechanism seems quite important for handling longer sequences.
Right, these aren't just arbitrary choices. Now, Table 4 is an ablation study on Yaad, basically stress testing it by removing parts. What happens when things like the retention gate or parts of the Huber loss are removed, or if the MLP memory is swapped for something simpler?
The ablations in Table 4 really drive home how important each piece is for Yaad. Take out the retention gate, performance drops noticeably. Make the parameters input independent. Performance drops. Remove the U1 or U2 parts of Huber loss. Performance drops. Replace the MLP memory with a simple linear layer. Performance drops again.
So basically, all those design choices actually contribute something meaningful.
Precisely. The retention, the input dependence, the specific loss function, the nonlinear memory, they all work together.
One last technical point.
Yeah.
Parallelizable training. Crucial for big models. How do they make these Miras variants faster to train? Something about chunks.
Yes, speeding up training for these recurrent style models is key. The basic idea, building on earlier work, is to break the long input sequence into smaller chunks.
Yep.
Instead of computing the state dependencies step by step through the whole sequence, which is slow, they calculate gradients within a chunk based on the memory state from the end of the previous chunk.
So it breaks the strict sequential dependency within a chunk.
Sort of. It linearizes the computation within each chunk, allowing parallel processing across the chunk's length. There's still a dependency between chunks, but it massively reduces the sequential bottleneck, making training much faster on parallel hardware like GPUs.
Got it. So wrapping up this deep dive, it feels like this research really presents a significant shift, doesn't it, in how we understand and even design sequence models. The Miras framework seems like a powerful tool.
I agree. It offers this unifying lens, clarifying connections between existing models, but more importantly, it inspires these genuinely new approaches to memory and learning.
And the core ideas, thinking about attentional bias as the main objective, reframing forgetting as active retention, coupled with the strong results from Moneta, Yaad, Memora, it's compelling.
Absolutely. The performance, especially on those key benchmarks, and the scaling with context length provides solid evidence for these new design principles.
And that ability to handle longer context better, shown in the scaling and the NIH results, that's a huge deal, right?
Yeah.
Tackling that long context challenge is critical for so many AI applications.
It really is. And the ablation studies just underscore how carefully you need to think about the interplay between memory type, the bias objective, and the retention mechanism. They're not separate knobs, they're interconnected.
Definitely a field moving fast. These technical concepts lay some really interesting groundwork. Thinking about it now, what aspect of Miras, or maybe the performance of these specific models, really grabs your attention? What technical questions pop into your mind?
For me, it's probably the potential for exploring even more diverse attentional biases beyond Null or Huber. What other loss functions could capture different memory properties, and how far can we push the complexity of the retention gates? Those seem like really fertile areas.
Good points. Lots to think about there for future work. We definitely encourage listeners to check out the paper itself and the wider literature. This is fascinating stuff. Thanks for joining us on this exploration for neural intel.